All right. Welcome everyone to the second episode of TRN Paper Dialogues. And this is a conversation series from the Transportation Research Network where we sit down with the authors of papers we've found thought-provoking and tried to get behind the scenes. And I'm Jiwon Kim from the University of Queensland, and I'm joined by my co-host Seongjin Choi from the University of Minnesota. And today we are hosting Professor Michiel Bliemer from the University of Sydney. Michiel is a professor and chair in transport and logistics network modeling at the University of Sydney Business School. He is a very well-known, internationally recognized expert across several core areas of transportation, including traffic assignment, simulation, travel behavior, and discrete choice modeling, and road pricing, and much more. And the paper we are discussing today is a novel mobility consumption theory for road user charging, co-authored with Alistair Loder and Zheng, published in Transportation Research Part B in 2024. The paper introduces a new concept of mobility consumption and develops a theoretical framework for measuring how road users use the road networks and how this can inform the design of road user charging schemes. So, Michiel, thank you so much for joining us. And before we dive into the paper, could you please give a brief introduction of yourself and your research, and then give us a short elevator pitch on the paper so we can have this shared context about this work?
Yes, glad to do this. So thank you for the invitation. So my name, as mentioned, is Michiel Bliemer. I'm the co-authors, as mentioned, on this paper. This was originally an ISTTT paper that we presented in Michigan. So for my pitch, I would also probably use some slides from that ISTTT presentation. I think this topic is close to my heart because it considers road user charging, which is something that I've been looking at for a very long time, for decades. But it is also relating to traffic flow theory. And this paper essentially merges the two into a completely different way to think about how do we measure road use. Because road use is typically thinking of distance is the amount of road use you have. But we argue in this paper that's incomplete. And I will try to explain with a little pitch why I think a different way of looking at road use is useful. So it came about as an equivalence between transport and energy systems. So on the left-hand side, we have road transport. On the right-hand side, we have electric energy. And power consumption, as we know, is measured in kilowatt hour. And this is usually what we pay for. We report how much we have been using, and therefore we pay this much per kilowatt hour. We argue in our paper we should be doing something similar in road transport, where we have mobility consumption measured in kilometer hour. And I'll explain in a moment why kilometer hour makes sense. And it would work in exactly the same way. You report how many kilometer hours you have consumed of mobility, and you pay accordingly. So how would that work? Well, let's think about mobility production and mobility consumption. So think of a single road segment that has a certain length, let's say 1 kilometer. With that 1 kilometer, we can produce for 24 hours per day a certain amount of mobility on that road. That's indicated with this rectangle. So the area that is indicated here in gray is the mobility production of this specific road over a specific period of time. So you can consume all of it if the road is used for 24 hours by vehicles at all the time. The mobility consumption, this is the novelty that we propose, is the amount of safe space headway that you reserve while you're driving. So when you're driving, you have some space to the vehicle in front, indicated here by these two red lines here, that you need to keep a distance to be safe, and that's the space you reserve exclusively for yourself. You don't want anyone else to come into that area, and if they do, you brake again to reserve more space. So this is the space that is exclusively for this vehicle. So if we draw all kinds of trajectories in this rectangle, you can see that this vehicle consumed this area, this gray area, another vehicle consumes this area, and that is including the vehicle length and the space headway in front of them. If we consume everything, then the consumption will be the same as production. For example, if we have a completely congested road, then the whole area here would be gray, where all the space is occupied by vehicles and their headway. So if you have a vehicle at a low speed, you have the vehicle length plus a small amount of headway that they reserve, but you have that over a quite long time because they drive at a low speed. So this gray area is the mobility consumption of a vehicle at a low speed. Similarly, you can have a vehicle at a high speed. They traverse this link at a much smaller amount of time, but they consume a much larger headway during that period of time. So here again, the area in gray is the consumption of the mobility. So if your vehicle at varying speeds, then the vehicle goes slow, goes faster, and in the end you just follow the trajectory of the vehicle and you have larger and smaller headways, and again you get this gray area that defines the mobility consumption of this vehicle on this specific road segment. And you can do this for every single link in the network, and you can calculate the total mobility consumption, for example, in a whole city, as well as the mobility production of the whole city. So this is the key equation. It's a very simple equation, but it's a very interesting equation. So what we're arguing is that gray area that I showed you earlier, that's now here in pink, that's the mobility consumption, and we define it as the cumulative reserved space headway over time for every vehicle. And the space headway we call h. So h is the amount of space, it's this little red vertical distance, is the space headway plus the vehicle itself, because that's included in the space headway. And if we integrate that over time, we get a very interesting equation. We get that you can write the cumulative space headway over time as a weighted sum of the travel duration, this is the travel time of the vehicle, and the travel distance of the vehicle. And then multiply with specific factors that are observable. For example, lambda here is the minimum space headway of a vehicle. And tau is the minimum time headway of a vehicle, also called the reaction time. So these are observable physical weights. The weight for the duration of the time is in terms of kilometers, and the weight in front of the distance is in terms of time, and therefore you get kilometre-hours. So this follows from the cumulative reserved space headway over time. And then two more things that I want to then show. So then we have this basic equation. We can calculate the mobility consumption of an individual vehicle and charge accordingly based on how long they have been driving and the amount of distance they have been driving, depending on something that relates to the vehicle, for example, the vehicle length, and something that depends on the reaction time of the driver. And if you then look this, for example, for my own trip, so this comes from my car. My car reports in my board computer every trip that I've been making. I can look at what was the duration of a trip, and I can look at what is the distance of my trip. I can put that here into the distance and in the time, and I can calculate therefore my mobility consumption for my journey has been 0.029 kilometre-hours. So that's in a nutshell the new concept of mobility consumption.
Very interesting. I think when I first read the paper, my first reaction was, this is such a great way, like very elegant way to frame road use, and it wasn't very obvious until I read this paper, but it kind of clicks into my mind, and then kind of naturally I can naturally adopt it because we are all users of the electricity. We are really familiar with this concept. So what was the how did you first come up with this idea of kind of having this electricity versus mobility type of analogy, and then from there, how did you kind of collaborate with the other authors to get this equation and then build up the theoretical framework about this idea.
Yeah, so I don't quite remember how I came about with the idea, but it has always been in my mind. We pay for water as water use, we pay for electricity, and road is just another utility that we want to pay for. And currently we pay it in a very complex system of fuel excise taxes and motor vehicle taxes. Why not just calculate exactly what we're using for? So I think about 10 years ago, I tried to make a relationship with electricity, and I was thinking about what's a transistor, what's a delay, what is the comparison then in electricity network. So you have heat in energy systems that is the same as delay in transport systems. So we tried to make all these analogies, but I got a little bit stuck. So this is where some of my collaborators came in. I was visiting in 2017 ETH Zurich for my sabbatical, and I met Alistair Loder. He was at the time a PhD student of Kai Axhausen, but his background was mechatronics and energy systems. And we started talking about, okay, what is thermodynamics, what are the laws, and we went very deep into the energy thermodynamics systems. And together we started developing these analogies. But the core that we always had from the beginning was we need to somehow relate it to kilometer hours. The kilometer hours was something that was more or less where we settled on. But the analogy was not clear at that time. So we kept progressing this work. And then at some point we thought we need to have these parameters. We need to have the lambda and the tau. We need to have the minimum space-head way and the reaction time. And this is where Zheng came in. He is at the University of Queensland. He is an expert in data analytics as well as car following theory. And he contributed to bring in this traffic flow perspective from a microscopic point of view. And together we essentially made this analogy. We expanded it to how would we then apply it to road user charging. Because measuring mobility consumption is one thing. Then you have a number, kilometer hours, but you need to use it for something. We thought the obvious use would be road user charging, because here the interesting part is, since you have road user charging expressed in a weighted average of distance and duration, that means both of them are fairly easy to obtain. But the duration part is new. Typically we only look at distance, but now we also have duration. If you look at duration, you essentially also get a sort of congestion charging mechanism automatically. So if you decide to drive during peak hours, you will take more time to travel and therefore you will pay more. So without a very sophisticated GPS system with time varying road user charges, you can actually still get that mechanism of paying for time. And this is also relating to how you pay, for example, for a taxi. A taxi is also per distance and per time. So there is some elements here that are more familiar.
And I really like this idea of this comparing this electricity and this road consumption. And I have some question related to this analogy though. So in electricity, the power, the way that this bill is calculated is based on how much you use that power and also how long you use, right? So there's a power and time played together to complete your consumption, and they are kind of independent, right? How how much power that you use, how bright your light is or dim light is, or how long you use. These are two independent things, right? But in mobility, I feel a little bit different because the way that now consumption is calculated is based on both distance and time. And usually this distance and time are correlated, right? The longer you drive, the longer you spend in terms of time. So I was wondering whether this correlation between distance and time, measuring this bill, have some implications in terms of this exact analogy.
Yeah, I think that's a very interesting question. So let's have a look maybe at some figures and equations we have in the paper. So we have in figure number tool. Is this tool? So here we have the space headways, and if you have free flow, you have more space headway than if you are in congestion, for example, in this area here, then you are driving closer together. But if you think about the definition of the mobility consumption, so I go to this equation here, equation number 2. If you think about energy, the energy is the integral of power over time. And power and time are independent, as you say. In our case, we have an integral over the space headway over time. They are essentially also not directly related, because you can drive on a motorway for an hour to your destination, or you can drive on a motorway for 5 minutes to your supermarket. So the time that you spend driving at a certain speed are independent. And therefore there is the same independence between the amount of space headway that you have, as well as the length of your trip that you drive at. So the space headway does have the speed in it. And that's where your argument comes in. So if you would drive faster, then you also have less time. And that's where some of the correlation indeed may come in. But I think the correlation is very small, because you can drive on the same motorway with the same space headway for 1 kilometer or for 1,000 kilometers. And these two measures are completely independent. How long you drive on the road and what speed you drive on the, so what destination you choose and what speed you drive at. But there is some correlation, I agree with you, because the speed is part of the space headway, which is not part of the power in electricity networks. Then the question is it a problem? I don't think there is any problem here, because this is the final approximation that we're getting if we're assuming that the space headway is linear related to the speed. But this is the equation that essentially is the analogy. And the space headway, in my view, can be completely independent from the time that you're driving the vehicle.
Yeah, I think that the integration part is very clear. And now when you have derived this form, now you have two components, time and distance. And that's where this confusion comes in, because we think that this time and distance are somehow correlated. But the fact that this has been derived from very clear integration of this one single term, that clarifies things. I think that that's, yeah, that's really interesting.
Yeah. Maybe can we go to figure 3 and have some discussion about this figure?
Yeah.
Yeah. I think this was the part I was keep reading and then trying to understand the idea. So can you first briefly explain what this figure is for the listeners of this series?
Yeah, so here you see 5 different space-time plots, each with multiple trajectories. So here we have, I think for each of the plots, we have 10 vehicles driving from this space, the upstream area to the downstream area. And this is free flow, so the vehicles here are quite far apart. They drive all at the maximum speed. And the gray area is the space headway, and the black line is essentially the vehicle itself, the size of the vehicle. So these are the occupations, the mobility consumptions in this space-time diagram. If we have congestion just at the capacity point, then all the vehicles are driving at, if we assume a triangular fundamental diagram, they're all driving at the maximum speed at capacity, where all their safe space headways are exactly connected together. So no one can come in anymore because they want to keep more distance. Here there's still vehicles that can go in between, here they cannot anymore. So this is at the point of capacity. But they're still driving in free flow, there is no congestion. But now suppose that there is a downstream bottleneck and that vehicles will be queuing, so they have to slow down and they will drive slower. So you can see from the trajectories, the speed is lower, and therefore they take longer to exit the road segment. If we just look at the area that this represents versus the area that this represents, then the common area is the light gray area here, indicated in 1. But the additional area is essentially this bit here, which is indicated here in area 2. So area 1 is mobility consumption that you always have, you cannot avoid. No matter what you're doing, you always have to somehow get from the one side of the link to the other. But this one is the additional consumption that you're having because you have a delay. And this goes into the mobility consumption of the time component, where you're not just the distance that you need to cover in this road segment, but you also have this delay due to the downstream bottleneck. And that's an inefficiency in the system. And that means, therefore, that you need to penalize people because they're occupying that road for longer, and therefore other vehicles cannot use that road space at the same time. And therefore, in this case, the consumption does not go directly down, but there's a little bit of a tail of vehicles that keep lingering because they're driving at a lower speed, they're queuing. And therefore they use more mobility consumption, and we believe therefore they also have to pay more in road user charging.
Yeah, I think this is very clear, and I think panel A and B are clear because we can understand that we are paying for the headway that we're occupying in this time-space diagram. But things are a bit more interesting if we look at like panel C, D, E, where it's congested. So my question is, let's say we have two drivers, and we have one that's driving in the at the front of the platoon and one that's driving at the tail of the platoon. We know from like traffic flow theory, by doing some like very small deviation of the front vehicle kind of affects the following vehicle and kind of can create some kind of phantom jam or something. Or maybe this congestion is due to some like a capacity drop due to like lane closure or something like that. So in this case, the driver in the back may argue that I didn't create this congestion because this was created in front of me by the drivers that's driving in front of me, and then I'm just taking the queue or taking the congestion that's just given to me. So, but in this mobility consumption theory, I think what you're saying is this driver who's driving in the back of the queue should pay more because they occupy the road and then they occupy more time. So can you do you have any thoughts on this kind of idea, or can you kind of clarify a bit more for me?
Yeah, so this is a bit of an economist view that I'm proposing here as well, is that if you are putting your vehicle on that road and you are spending more time on that road, that means that you're occupying the road for longer, you still need to therefore pay for what you're using. I can understand your argument. This is, of course, a very stylized example where there's no one behind you, which is this will not happen, right? That you have suddenly a queue and there's nothing anymore. So there will be vehicles behind these other vehicles coming. The first best pricing principles will then dictate that because you're driving there, you will also cause delays to the vehicles behind you. You have to pay for these external costs, and that is what you then also need to pay for. So if there's no other vehicles behind it, I can understand your argument. It would be perceived as unfair. But I would argue in reality, there will always be vehicles behind you. You will be hindering those vehicles, and suppose that those vehicles will be 2 seconds delayed, very little, because your vehicle is there. But there's hundreds of these vehicles behind you. Therefore, there's still a significant amount of delay that you cause to other vehicles. And therefore, in this case, I think you would still want to charge people for road use because they are occupying that space for longer. And they could also choose another route and maybe be faster.
Mm-hmm. Yeah, I think this is a very, very important behavioral question, right? So I think people now have to care more about time that they are spending, not just the distance. And I think that another related question from here is that this somehow now similar to the existing time-based charging. So there's a kind of time-based charging as well. And one criticism or some concern from that was that now because people are caring more about reducing time, they are doing more risky driving behavior, right? So I wonder whether this mobility-based charging also have that similar concerns.
I have a couple of answers for that. So the first answer is taxi drivers already do time-based charges. I don't remember that I ever asked my taxi drivers to drive faster. The second one is risky behavior. Well, we do have speed limit laws that you cannot exceed the speed limit, but suppose that it does induce some risky behavior. The question then is, are the distance-based charges outweighing the time-based charges? So I have here also some slides that I would like to show you. We did some calculations of how much would a kilometer cost and how much would a minute cost. So let me show you what we came up with. So we took the example in Australia, New South Wales specifically in Sydney, and we converted all the fuel excise taxes and the motor vehicle taxes into a kilometer rate and into a minute rate based on our mobility consumption theory. And based on these fuel excise taxes and other taxes, we calculated that we need to charge to be revenue neutral, to essentially let the car drivers on average pay exactly the same as before. We need to have 5.67 cents per kilometer and a bit more than 3 cents per minute. This is Australian dollar cents, so US dollar is slightly less. What you can also then see is the amount of kilometers that an average car drives and the amount of minutes that a car drives on average. Surprisingly, they're quite similar. So they're almost the same numbers. But if you then do the calculation, you can see that the distance-based charges are about 2/3 and the time-based charges are about 1/3. And therefore the distance-based charges always outweigh the time charges. So the first argument that I refer here to Bonsall and Palmer, the distance-based charges should exceed time-based charges to avoid the driver's focus on minimizing travel time through risky driving. Exactly as you say, if we can somehow not have too many of these time-based charges, it should be okay. But this is a statement that has not been verified. So we don't know. I have another answer then, is if we look at how much time you can save, suppose you're driving on a motorway and through risky driving, by being aggressive in your driving, speeding a little bit, you are 5 minutes faster to your destination. That would mean, according to these numbers, that you save 15 cents. I would argue that's very little. There's very little gain to just do risky behavior. If we compare it with the value of travel time, which is an important measure in travel behavior, we know that in Australia, people value their travel time as about $20 per hour, Australian dollars. This is 30 cents per minute. So actually the value of travel time that people have inherently in themselves, if they can save 5 minutes of travel time, is worth much more to them than paying a 15-cent charge on top. So the value of travel time completely dominates the charges for the minutes. So I think that's another argument to say this is probably not going to cause a lot of risky driving behavior because it's so minor. The last answer I have is we're going to test this. We have received funding from the Australian Research Council to do a driving simulator study and observe what people do in different situations. And we're going to have a field trial in Sydney with 100 drivers where we get all the GPS data and we give them different distance and duration rates. And we try to observe with the GPS data whether they actually change their speeding behavior or not. And we'll match it to the speed limits to see if they're actually more exceeding the speed limit. My hypothesis is they will not. But as I said, we don't have evidence yet. and this hopefully comes from a driving simulator study and from our field experiment.
I think that related to this, can you go to the case studies? And I think that this also was demonstrated in that case studies where incorporation of these time components actually benefits.
So you mean section 5.1?
Yes, it says 5. So there's two case studies in this paper, right? So could you briefly, just briefly explain what these case studies found?
Yeah, so we tried to look at two very basic travel behaviors. The one is departure time choice, would that change? And the other one is route choice, would that change? So the first situation is a very simple bottleneck model, Vickrey's bottleneck model that's well known to many people. And the second network is a very simple two-route choice example where we try to see what happens in this case. So just to look at the basic behavior. If we look at the departure time behavior, if you only charge for distance, there is no way that any pricing will matter. So in this case, people will still behave in the same way. You cannot optimize the system by charging per kilometer because the distance is always the same. But if you charge for distance and for time, for duration, then you can obtain better outcomes. You can actually decrease the travel time. So we have a figure here that relates to the bottleneck model. If you don't do any charging or you do distance-based charging, you're on the top of the line, you have your maximum delay. But if you impose some additional cost for travel time, then people will have more peak spreading. They will be more flexible, they will be leaving before or after the peak to minimize also their duration charges, and therefore the total queuing delay in the system will decrease. So here mobility-based charging will help to some extent in getting a better outcome for everyone. The second is route choice. If you think about kilometer charging, which is what most people are proposing, and there's all kinds of countries that have already implemented it for trucks. If you are only focusing on distance, what you could expect is if drivers want to go from this origin to this destination, they choose the shortest route in distance. They go straight through the suburbs to residential areas, through the city center, with all low capacity roads, because that distance is shorter and they can save money. But that's probably not what you want, because there may be a motorway around the city center that is much longer, but high speed. This is a motorway. But you will penalize that by saying, no, we're charging for distance. So we don't want you to take the longer motorway at high speed. We rather have you go through the city center. So this creates some perverse incentives for people to take maybe risky behavior in this way. Not time-based risky behavior, but distance-based risky behavior. And then we showed that if you do mobility charging, you can make a similar plot. If you have no charging, you may have the lowest queuing delay. If you do a lot of distance-based charging, you're sending everyone through the city center with a bottleneck and a low capacity road. So you have the maximum delay. And mobility charging is somewhere in between. So it doesn't have as much of that component, but it still has a distance component. So it will still have some distance-based charges that people will face, but it also has a time component that makes them more likely to go the longer route, but a faster route via the motorway. So those are the two basic behaviors that we analyzed in this section.
So I wanted to ask about how do we get the data for parameter estimation that's used in this model? You mentioned that two parameters you are using right now. One is related to the spacing that this cars are occupying, and one is related to the reaction time. And how do you, and it can be homogeneous across all different contexts, but I can imagine also like in some cases, for example, if you're driving in a motorway versus if you're driving in a like a off-road or rural road, or if you're driving a truck versus if you're driving a personal vehicle, these parameters are would be different. So what kind of data can we use to get these kind of parameters, and what are the good pipeline to estimate the parameters that we use in this model?
Yeah, so the two basic parameters that we have, the minimum space headway and the reaction time, are fairly easy parameters to get because they have been widely reported in many studies. So the reaction time is usually somewhere between 1 and 2 seconds. It may depend on the driver. It also may depend on the braking behavior of the vehicle. So a truck needs much more time to stand still, so they need a longer reaction time. And the other parameter, the minimum space headway, is very much dependent on the size of the vehicle. So a truck or a bus will have a larger value there than the car. So we mainly focused in this paper on car traffic, but for any other vehicle, you can do the same analyses. And here we have also some plots in the paper where we looked at the 𝗀𝗄𝐶 data to see what type of vehicles do we have. We have different vehicle lengths, as you can see here. So we have all the way from cars on the left to larger trucks here on the right. We looked at the time headway they need, the minimum time headway they needed. So the ideal data that we would like to have is individual trajectories. So like the 𝗀𝗄𝐶 data, data from drones, data from cameras and video, and that we can analyze to see how far do people drive apart, what is the headway for different speeds, and the vehicle length is of course an easy one to observe. So we looked into the literature and the numbers that we report in table 3 here. Let me make it a little bit bigger. They we took from Ma and An, who also analyzed the 𝗀𝗄𝐶 data. And what they found is the average reaction time is about 1.23. But other studies may have slightly different numbers, but it's usually around 1 or 2 seconds. The average vehicle size that was observed is usually somewhere around 5 meters. And you need to add to that the bumper-to-bumper spacing to get the space headway. So we have the vehicle length plus the bumper-to-bumper spacing that you need to add to it, which is about, in total, 11 meters as a minimum. If you have all the vehicles standing still, you need about 11 meters for each vehicle on average that we observed in this data set. What we would like to have is more data that is on different types of roads, not just the motorway, but also on urban roads. We'd like to have data of free flow and heavily congested roads. So the data is still limited, that we usually only have a few types of roads, usually just motorway, and we only have a few types of congestion levels observed. We don't have the whole range from free flow to all the way to standstill. So ideally, you would have that whole range to determine what values are the best to use. I'm not saying that these parameters should vary according to location where you're driving, because that complicates things a lot. I would say every vehicle has one value for lambda and one value for tau, and that's the values that you assign to them. But they will be vehicle specific, but not road specific. I don't think that it makes sense to make it that complicated, because we also need to explain that to road users. If you want to explain to road users how they're going to pay, it needs to be simple. It needs to be able to be transparent. And if we add duration to the travel distance, that's already a complication factor. So I think going further than that and having more parameters for each user probably is going too far.
So in terms of this, the lambda and tau, which determine this purely consumption level, right? How much you consume in terms of mobility consumption.
Yes.
The parameters determine. But on top of it, we also need to have another parameter to make this actually charging. So there's equation 4 that you now have based on this much consumption, how you will actually charge, right? So that parameter, which is now mu and delta, right? So that's actually probably what people care more, because that determines how much you pay. So based on your consumption, do you also think that that should be universal, kind of uniform across regardless of roads, or it should be more context dependent?
Yeah, so here we multiply the mobility consumption with a charge C. C is the rate that you pay per kilometer hour. And that could be vehicle dependent. So N, the subscript N is a vehicle. If we have an electric vehicle, maybe you want to charge them less than if you have a petrol vehicle. Or if you have a heavy vehicle, maybe you charge them more than a lighter vehicle. In Australia, we usually charge vehicles more in the motor vehicle tax if they're heavier. And we give discounts if they're electric. So this parameter you can play with the C, you can play with for each individual vehicle, because in Australia we already have vehicle-specific charging rates. Also, of course, fuel excise tax also depends on the engine type. So that's also essentially automatically vehicle dependent. So I think how we determine them in this paper is using the concept of revenue neutrality that I mentioned earlier as well. So if you want a road pricing charging scheme to be acceptable to both the public as well as the politicians, you only have one choice, which is revenue neutrality. Because if the government would get less money, they're not happy. So they want, if you change the system from fuel excise tax to motor vehicle tax to a different system, mobility-based charging, then they still want to have the same revenue. Equally, if you charge them more, the public will not be happy because they're saying you're trying to get us, you want to charge us more. So for them, if you charge them exactly at the same amount as previously for the average driver, that is acceptable to both parties. So in this paper, we looked at revenue neutrality. What does an average car driver, in our case in Sydney, currently pay for an average car? And we set the C rate, the congestion charging rate, exactly such that an average driver would pay exactly the same. And that's how we determined the C. But as I said, you can give discounts for different electric vehicles, for example, or you can have them paying more depending on their weight.
Okay. So in this paper, this case study and context is focusing on this the pricing, right, charging. But I think that this idea of this mobility consumption theory, I think that it can be applied a lot more broadly in different areas as well. So could you share your thoughts about some other applications beyond this pricing?
Yeah, so the most obvious one was the road user charging. And the other one that we're thinking of is probably traffic management. So if I go back to an earlier picture that we discussed, this one, we can see that this area here is the additional area that we are charging people for their road use because they are delaying and therefore you need to pay more. This is like congestion charging. If you would try to minimize this whole area, so if you want to minimize the mobility consumption, you probably also get something similar to minimizing congestion in the system. So it could be used possibly as another objective for designing a network or for routing, and in our case for charging. So I think traffic management here could be another potential application area where you try to minimize all these additional areas too. Another thing that we're thinking of is looking at our equation for the cumulative space headway, where the space headway is a function of the speed. There's also an interesting relationship with energy consumption. So we later in our paper, sorry, a bit scrolling fast. Later in our paper, we also briefly touched on different engine technologies, and this is not entirely clear yet. This is just a small paragraph that we added, so we need to look into this. But we also observed that the faster you drive, the more energy or more fuel your vehicle consumes. And therefore you have a similar relationship that you can then use to calculate the energy consumption in exactly the same way as you have your mobility consumption. And therefore you can add your energy consumption and have emission charging on top of your road user charging. So we just looked at charging for road use and we ignored everything else. But if you also want to charge for safety or for emissions or other components, we could possibly add that to such a system if it is depending on the speed. And the third area we were thinking of is, can we expand this to public transport? Can we expand this to active transport, to cycling, and measure their road use and optimize it for them? It's a bit trickier because cyclists do not necessarily have lanes. They may overtake, that's more chaotic, and like pedestrians, they don't adhere to lanes either. Our measure is very lane-based. We're assuming you have a reserved space headway within your lane, but if you don't have lanes, that becomes more complicated. So would this, for example, this theory also expand to 2 dimensions? Could we also come up with a different application area for active transport? We haven't looked into it yet, but those are the areas that we're thinking of.
I've been actually thinking about this network design that you mentioned, because this mobility-based charging gives drivers a real incentive when they're adjusting, rerouting, or diverting to find a faster path to lower their consumption. But then that only works if the network actually gives such opportunities, right? So when you are stuck in a long stretch of freeway with no exits, the driver is stuck in a queue and has no way to act on the price signal, right? So they will just sit there and then pay more. So I was just wondering whether this theory, if we are using this theory in thinking about this whole system of production and consumption, whether it implicitly favor networks with more connectivity, adding more entry and exit points, or more route alternatives so that the incentive can actually be acted on. So do you have any thoughts on that?
It's an interesting question. I don't have the definite answer about it. So if I think mostly about what often happens now in system optimum calculations that people use road network design for, they try to minimize the total travel time.
Yes.
And we're arguing here that's incomplete. You need to minimize the travel time and you need to minimize the distance as well. What that would lead to a network, if I think about current mobility production, essentially during the night, there's all these roads that are empty. They're producing mobility, but nobody's consuming it.
Yeah.
I think if you want to really reduce the amount of waste that you have in your network, you actually want to have less roads. And you want to only focus the roads on the major routes and not build anything extra really. You just want peak spreading to happen. You want people to spread across routes. You want people to spread across time, but not have too much redundancy in the system because that's all wasting production. So I wonder if that could be an outcome that it says if you optimize for mobility consumption, that in relationship to mobility production, so the loss between them, that you get a very different network, and maybe it is a much smaller network.
Yeah.
Because in electricity networks, it works a little bit different. They only produce just enough as the demand is. So we all know that there's peak periods for electricity consumption, and the power generators just produce just enough. Because if they produce more, it goes to waste. You cannot easily store it in big batteries. But for infrastructure, that's very difficult. Once you build a road, it's there and it's producing mobility all the time, and it is a waste if it's not being used. So it is very hard actually to reduce the waste if you have peak travel. So the peak travel is really the problem. It's very hard to solve with road networks.
Yeah, thank you. Okay, so let's say if a PhD student read this paper and want to, you kind of laid out some of the other applications that this theory can be applied. But if someone read this paper and then want to kind of push forward on relaxing some of the assumptions you made in the paper, or try to push the idea to something deeper in the theoretical aspect, what are some recommendations you would have to those students who's reading this paper?
Yeah, there's some hints in this paper. We hint a little bit at engine technologies. We hint a little bit at connected autonomous vehicles. I think the CAVs, the connected autonomous vehicles, are an interesting one because they have very particular values for example, reaction time. If you have platooning or if you have coordination between vehicles, you can very much reduce the mobility consumption footprint with CAVs. That is completely non-explored in our paper. And I think that's where you can have a massive gain in mobility consumption minimization. So that would definitely be an area that I would recommend people to look into. Another area is behavior. As I mentioned, we're going to do some driving simulator studies to just see if we charge for duration, will people actually have speeding behavior or not? We don't know. What we also don't know, if people find it acceptable to be charged also a time component. We don't know if people understand this system, the space headway, or are they happy to just assume, okay, I have a kilometer rate, I have a minute rate, and that's all they need to know. So I think in terms of acceptability, transparency, and behavior, I think there's a whole area that you can research. Also, the network effects of this is something that we have started now to look at it. What would happen if we implement this on a larger network? We've done some traffic assignment runs on some networks across the world. That's also something that we don't know yet, whether it actually will make the system better or not. Will it increase the congestion? Will it decrease the congestion? So we're looking into all these different areas. So there's still so much to be explored. This is the first paper of its kind that was published. And so far, the only paper that we've published on this topic. So there is a lot to look at.
Right. So thank you very much. I think it has been a really rich conversation. And I think before just we close, I would like to ask one last big question. And after all these years of working on these various topics in transportation, why do you think this transportation is still interesting? And what is it about this field that keeps you curious? Just your general kind of view and vision in this whole transportation research?
What really fascinates me about transport is it has the physics component and it has the behavior component. So if you just observe water flows, the water goes where it goes, and you have all physics involved. The same with all kinds of other civil engineering research. But transport is different. Transport has not moving water or moving particles, it's moving humans. And humans are unpredictable. They may accept it, they may not accept it, they may disturb the system. But we can also influence their behavior with incentives, by pricing or rewarding. And I think that makes it very fascinating, because also what this paper highlights is there's a physical component and there's a behavioral component. And that you find almost uniquely in the transport field. In civil engineering, that's the only one I think that does have this interest. So that's why I work in both areas. I'm very interested in the network and traffic assignment and the traffic flow, but I'm equally interested in the travel behavior, choice experiments, discrete choice models, to find out how people respond on a micro level within such a system. And that to me really is driving me in this area. That makes transport for me very, very interesting.
Yeah, I think that in that sense, this paper is really the crux of this whole, all the things that you just mentioned, and it has a behavior, it has a traffic flow theory, and actually it really gave us new ways of thinking about this whole mobility. Although the paper is about consumption theory, I was really fascinated by this idea that it was actually production. We were thinking that we were just using this infrastructure, but we were actually producing whole mobility, and then this is there to be consumed. So I think this is a really interesting and intriguing idea. So thank you very much, Michiel, for sharing your insights behind this paper. And also on behalf of this community, I would like to thank, and also I look forward to more follow-up studies like this from your group and then your the work. So thank you very much.
My pleasure. Thank you very much.